Okay, so we got a couple of learning goals today. First one is to be able to calculate the derivative of a polynomial. The second one is to be able to find the equation of a tangent line or a normal line to a given point on a curve. And this is going to be our homework. So, a little bit of a preview. Over here, we've got a lot of functions. And over here, we're going to get the derivative. So, for example, if your function is 5x cubed, the derivative is 15x squared. If your function is 7x to the fifth, the derivative is 35x to the fourth plus 2. I'm going to hide the rest of them, but you might start seeing something. You might make a hypothesis of like, I think here's the pattern. I'm going to show you how you get the pattern, and then we're going to show you the shortcuts so you can skip the pattern. So this is our derivative definition. The derivative, dy dx, which also could be like f prime of x or y prime, also totally okay, is the limit as h approaches 0 of a little bit bigger than my function minus my function divided by h. This is super connected to that image that we had of that triangle. Looked kind of like this, where if this is our x value right here, and I want to know what's the slope at that point. That's my goal right here. I want to know what's the slope. One way to do that is to go a little bit bigger than that, and then draw this lovely triangle. And we should be able to, without too much trouble, calculate the slope of that hypotenuse, which is almost the slope of that curve. And as this triangle gets smaller and smaller, it works. Well, let's call this distance right here h. That means that this is going to be like x plus h. So if x was 1 and we meant h1, then this would be 2. If x was 1 and this was a half, this would be 1 1/2. This value right here is going to be f of x. And this value right here is going to be f of x plus h, whatever value I'd put in there. And so this right here, which is our rise, would be that. Literally, the bigger value minus the smaller value. And the run is really just the distance of h, which if you wanted to, you could think about this as like x plus h minus x, because that would be this value minus this value, which gets you this distance. But I think it's probably a little bit easier if we just leave it as is. Okay, so that's the visual. Let's get the algebraic. So I'm going to use this function. We're going to call f of x is 5x cubed. If I want to use this function to get the derivative of this, that's what we're looking for. We want the derivative here. What I need to do is I need to also get f of x plus h. Well, in that case, I'd have 5 times x plus h cubed, which I could expand, like so. And then I'd have f of x, which is this, f of x plus h, which is this, and I have all of the pieces that I need. So if I start putting this together, what I'm going to get is this bit right here, which is f of x plus, oh, man, let's try that again here, f of x plus h and f of x. So I'm going to take those pieces. I'll just clean this up just a tiny little bit, because apparently I write sideways. Okay, so what we're going to look for here is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, well, I can simplify this. 5x cubed and 5x cubed simplify each other. And then if you notice, I've got an h in each of these terms. So I'm going to factor out one of those h's. And what you'll get is that I can simplify the h in the numerator that I just factored out and the h in the denominator. And I am left with this, 15x squared plus 15xh plus 5h squared. Well, what I care about is as h gets closer to 0. Now, when h actually gets closer to 0, we end up dividing by 0 and everything falls apart. Go back to the image before if you want to. But if this is basically 0, this whole term basically becomes 0. Same thing here, this one basically becomes 0 because you're basically multiplying by h. Now, I'm being kind of hedgy with my words because I can't just say you're multiplying by h because you're not, but you're getting real close. So, all you have left at the end is the derivative, which is just 15x squared. Now, that was a really long explanation for a very simple pattern. So let's go back to that table that we just looked at, this one, and let's see if we can figure out the actual pattern. So 5x cubed becomes 15x squared. 7x to the 5th plus 2x becomes 35x to the 4th plus 2. Negative 2 x to the 8th plus x to the 5th becomes negative 16. And hopefully you're starting to see a pattern here. And really what it is that this 35 comes from 5 times 7. You're going to multiply those. And the reason this is a 4 is because it's 1 less than 5. 3 times 5 is 15. 3 minus 1 is 2. So here we're going to get 7 times 10, which is 70, x to the 6th, because if I take away 1 here, minus 12, x to the 3rd. Cool. Here, if you just had x to the 9th, you'd get 9x to the 8th. And the reason that we've got this like 1 here is because sometimes people are like, well, where did the 9 come from? It's because the 9 has to multiply with a 1. And in general, if you have x to the n, your rule is always going to be multiply, make a coefficient out of that exponent, and then subtract 1 from the exponent. That's the rule. So you don't have to do all of that mess that we just went through. You just need this part. So if I was to look at this, here's the actual rule. The original function is this. Here's our derivative. G of x, this would be fairly simple. We'd take 4 times 7 and we would get 28. And then we would say x to the 6th because I'm going to take away 1 from 7. This, though, gets a little messy, and it's pretty helpful if you remember that I can rewrite this as x to the negative 7 plus x to the 5th, and then anytime you're raising something to a cube root like this, that's like the 1/3. So this is just k of x. I haven't found the derivative yet. The derivative, k prime of x, is going to be negative 7 x to the negative 8, because keep in mind, when you subtract 1 from negative 7, you actually go down to negative 8. And then here, this is like x to the 5/3. So we have like x to the 5/3. I'm going to add then 5/3 x to the 2/3, because the 5/3 becomes my coefficient, right? Because 5 and 1/3, that's 5/3. And then 5/3 minus 3/3, which is 1, is 2/3. Here is this. If you want to rewrite this now, you absolutely can. You could rewrite this and say, cool, k prime of x is equal to negative 7 over x to the 8th, just getting rid of that negative exponent, plus 5/3 cube root of x squared. Let me know what questions you have about that. Let's go on to tangent lines. Okay, so now you've got this lovely curve, and you've been able to calculate the derivative. You might need now the tangent line or the normal line. The curve right here is just the pink function, and we care about this orange point for whatever reason. The tangent line is going to be a line that goes through that orange point and has the same slope as the function at that point. The normal line has the opposite reciprocal slope. So here's the rule for this. So tangent line touches the function at only one point locally. The slope is whatever that is, a over b. A normal line is perpendicular, creates a 90-degree angle to the tangent, and intersects at the same point. So its slope is negative b over a. If you remember, these are opposite reciprocals of each other. So let's do a quick example of a tangent line. Okay, so here we've got a function, and we're going to find the equation of the tangent line to the point where x equals 2. So I can get that right now, let's get the point first. So the point. We need an x and a y, and we know that x is going to be 2, and we're looking for our y value. So let's figure that out. We just have to plug in 2. Do that, and we're going to get 14. So our point is 2, 14. Next thing we need is we need the slope. And to get the slope, we need the derivative of this. So f prime of x is going to be 2, because we'd have 4 times a half, which is 2. X to the third plus 3. And we now need that when x equals 2. So we're going to plug in 2. This is going to get us 16 plus 3, which is 19. So that is my slope at x equals 2. And voila, we have all the things we need. Now we're just going to use the point-slope form of equation. Y minus y1 equals m. X minus x1. You guys might have a different form that you like. That's fine. My equation is just going to be y minus my y value, which is 14, equal to my slope, which is 19, x minus my x value, which is 2. And voila, that is my tangent line. If I wanted the normal line, it's the exact same line, just y minus 14 equals 1 over negative 19 x minus 2. Because the only thing that has to change is that the slope becomes the opposite reciprocal. If you want to solve these for mx plus b, knock yourselves out. I don't really care. I mean, like, it doesn't matter. I do care. I just